Um, Thank you for inviting me. I'll be talking about geomechanical aspects of geological carbon storage. And first, I want to acknowledge some people who contributed to my education in this area. As was mentioned, I got my degrees, graduate degrees from University of Minnesota. So my two advisors for master and then PhD were Emmanuel Deterny and Joseph Labus. And then I really started working on CO2 storage when I was a postdoc in Lausanne and in Switzerland. And there were two people who helped me, or three people who helped me learning about it, including my advisor, Professor Lalui, and then Professor Padlachkov and Dr. Villarasa. And 4 years ago, I started as an assistant professor at the University of Illinois, and mainly working on, of course, rock mechanics and CO2 storage, and being involved in a few projects that were supported by the Department of Energy, Center of Geological Storage of CO2, and now a big project called Carbon Safe, Illinois. And it was my postdoc, also former University of Minnesota graduate student Ali Taroch, and also my first PhD student Kisok Kim, who also contributed to this presentation. So the motivation for storing something underground, and in my case CO2, is the significant increase in fossil fuel emissions by almost by a factor of 4 since 1960s. So, and especially accelerating over the last couple decades, and we've seen only a few, trends going down. One was in 2008, and one was kind of observed earlier this year, and now it's actually getting back. But of course, the industry was partially shut down due to the COVID-19, and now it's picking up. So the amount of CO2 in atmosphere is increasing. There could be different plots that I could show. I decided to show this one. And of course, it's because we need more energy. There are more people. We actually, there's more transportation needs. So all of this requires producing energy. It's mainly produced by burning fossil fuels. And when you do that, you emit a lot of greenhouse gases. CO2 is one of them. So some people do believe, some people don't, but it all contributes to the climate change. And at least the facts are that the amount of CO2 in the atmosphere we could track back almost a million years ago has never been like that. And also the temperature, the average temperature now is getting to the point that the Earth hasn't seen for at least last 500,000 years. And some people believe again that this contributes to the global climate change, and climate change by the means that the average temperature increases, and that produces a lot of problems for us. And to mitigate that, there are a number of now international commissions and meetings to discuss what to do. And of course, probably everybody heard about Paris Agreement, which basically it was discussed what are the potential scenarios for the increase of the CO2 emissions and increase of the average temperature on the planet, and then what could we do about that, because it's believed that an increase of more than 1.5 to 2 degrees Celsius will lead to extreme weather condition, to global movement of the population, and losing a lot of representatives of flora and fauna. So there are a few, of course, approaches to that, and one of them is to use more renewable energy, to use cleaner energy, like instead of burning coal, you would be burning natural gas that by the same amount energy produced would contribute to 4 times less greenhouse gas emissions. But also another thing is that we would still be emitting something, and the idea is that we can actually capture most of what is emitted and then store it underground. And I'm specifically talking about carbon dioxide, one of the greenhouse gases that contributes a lot to the increase in the temperature and bad environmental conditions. So CO2 can be captured at the power plants. It can be also captured in the atmosphere, but it's much more expensive and complicated. So it can be captured at the power plants. In fact, we're already doing that here in Champaign for the power plant that is producing electricity for the campus and surrounding neighborhoods. It can be captured, then transferred to a particular location, which should satisfy, certain geologic conditions. It's been found that the best and most available formations are deep saline aquifers. So the water from there is not drinkable, and at the same time there are huge volumes of CO2 that can be injected. And there are other options like depleted oil and gas reservoirs, coal seams, but we mainly look in the main contributor to it would be deep saline aquifers, and in fact they're available everywhere, almost everywhere on this planet. And so of course when we think about CO2, we think about the gas, and it takes a lot of volume, but the thing is that when we capture it, we can pressurize it, we can bring it to high pressure, a few megapascals, so a few hundred of psi for Americans, and then we can inject it underground, and starting from a certain depth, the pressure and temperature will be that high that it actually turns, so when we just pressurize it at the Earth's surface, usually it exists in a liquid state, so it's slightly less dense than water, and the viscosity is by 1 order of magnitude smaller than the viscosity of water, so it already flows well. But when we bring it to the reservoir conditions at higher temperature and higher pressure, it actually has smaller density, so we can inject even more, and also it has significantly smaller viscosity, so it exists in so-called supercritical state. And most of the times it's actually beneficial to bring it to the supercritical state, because we can then inject very large volumes and they would be flowing easily in the reservoir. So then when we inject, there are a number of things that are happening there, but basically 4 main mechanisms for CO2 trapping. So we are looking for the formations where there is a cap rock, so the low permeable formation that is on top of a relatively permeable reservoir, and this low permeable formation is supposed not to let CO2 to get back to the near surface and contaminate aquifers or just being again released to the atmosphere. CO2 is also trapped in the pores of the rock, in the small pores of the rock. It's a non-wetting fluid. With time, it dissolves in the fluid, like when you open your soda bottles or cans, that the gas that releases is CO2. So at high pressure, you can, in fact, at like reservoir conditions, 1/3 of the volume. So if you look at the brine, the saline water, in fact, you can inject CO2 and it would still occupy the same volume, but 1/3 of the volume of that brine could be actually CO2 dissolved in it. And then eventually, when CO2 is mixed with the brine, it decreases significantly the pH, so makes the fluid acidic, and that facilitates the reaction with the minerals that form the rock. And then, so you kind of precipitate and make new minerals, and that also allows CO2 to stay then in the reservoir forever. And of course, those processes all have different time scales and could be taking a while, but we will try to rely on all of them when trying to store CO2. And in fact, the first project that started really implementing this strategy was done in Norway, and it's still actually ongoing. And it was in Sleipner, so it's an offshore platform. And the motivation was purely economical at that point. Is that just in Norway since 90s you have to pay huge taxes for emitting CO2. So companies started looking for the options to do something with produce CO2 rather than just emit it to the atmosphere. And right now there are more than 100 projects that are sometimes going on, sometimes they're paused, but more than 100 projects were or are implemented. Most of them are small scale, so pilot scale projects, and like US has a lot of pilot scale projects. And again, we still see that even though the deep saline aquifers are available almost everywhere, then there are still some places that are, that where to inject CO2 is significantly more beneficial than in the others. Like, for example, Minnesota or in Wisconsin, they have a lot of basaltic rock and don't really have big, saline aquifers where you can inject. So on this map, there is not too much gray on their map to show actually good sedimentary formations. On the opposite, Illinois, Indiana have some very nice sandstones that could be the host for CO2 storage. And in fact, there are already a few projects that are being implemented in Illinois. So one of the other things that happened over the last few years was that, and I'm not, of course, the one who knows about taxes and economy a lot, but there is a 45Q credit. So this law was passed, and that what it says is that when a company decides to invest into storing CO2 instead of emitting it to the atmosphere, they can get a tax relief up to $50 per ton of CO2 stored. And that actually becomes economically beneficial, because now the price for storing a ton of CO2 is getting there. Maybe now it's still around $60, $70, depending where you are, but it's getting there. So in fact, what we try to implement in Illinois is to make CO2 storage economically feasible, and that actually means building, a network where we can transport CO2 from different power plants. Like I'm showing here the places, actually these black dots is where CO2 is or will be injected. Actually, these 2 points is where we're already injecting. And this is Champaign. This is Abbott Power Plant in just on campus of University of Illinois. And in fact, we're already capturing CO2 here and transferring it to here to inject it underground. But of course, we need significantly larger scale projects. And up to just recently, there were a few oil companies who actually seen that it could be economically beneficial. So they started drilling those wells. And this year we see less interest due to the economical problems, but I hope that we can quickly get back to it and then start really some large-scale CO2 injection. So Illinois industry is producing a lot, but we can capture and store almost everything and start actually doing it within the next few years. So this was kind of an introduction, and now I need to say something about geomechanical aspects. So of course, when you inject CO2 underground, it's not that it just goes in the formation and nothing happens. So here, I hope it's going to work, but I wanted to show some kind of quick simulation on that we did to show what really happens when CO2 plume is injected. So this is the plume. This is what happens to the temperature. And okay, and this what happens to, let's say, the vertical displacement. And of course, there are also deformations in all the directions. So basically, we can consider the problem, and our target reservoir should be confined by two low permeable layers such that CO2 doesn't actually leave it and stay there forever, letting all those trapping mechanisms to start acting. So it should have a low permeable cap rock. Usually it's a mudstone shale, and then it could have another, shale or even maybe some crystalline rock that will be the base here. And when you inject CO2, it's usually injected at a temperature lower than the reservoir has, so there is some thermal effect. Of course, thermal effect also produces the mechanical effect because the rock is either expanding or shrinking due to heating or cooling. You change the pore pressure because, of course, you inject some fluid. So you produce the changes in temperature, in mechanical stresses, and in pore pressures. And that's what is called thermo-hydro-mechanical coupling. In fact, another thing that should be added to this diagram is actually a chemical effect because with time, the pore fluid becomes acidic and starts affecting the properties of the reservoir as well as the confining layers. So last year, we published some kind of a review with my collaborators on what are the challenges of CO2 storage from already existing pilot projects and just kind of our understanding of the process. So so the main thing looks like it comes from inducing the seismicity, and I will talk about it in just a few minutes. But when you change the state of stress, when you change the pore pressure as well as the temperature, you change the properties of the rock. Sometimes you make it weaker, as well as you increase pore pressure. So you can actually make the rock to fail or yield, and that would produce the seismic events that we try to avoid. And then there are also other, of course, issues such that the CO2 can leak to the near surface, as well as in some cases it was recorded measurable surface upheave. So you inject at the depth of a few kilometers, and you still measure that your surface actually lifts up due to these storage operations. So we're trying to approach this problem mainly from the perspective of the characterization of the participate information. So here in Illinois Basin, we inject in lower Mount Simon sandstone, relatively high permeable material. It has some kind of intermediate material just underneath it, sandstone, but with clayey inclusions, less permeable. And then it has a very stiff and strong basement rock rhyolite. And we try to represent this in situ condition. So we inject at the temperature that we have there, around 50 degrees Celsius. We apply the vertical and horizontal stresses that correspond to the reservoir conditions, and of course the pore pressure, and we inject CO2. And then we have a few experimental techniques, including triaxial testing, core flooding, where we see what happens to our rock under this condition, not only the reservoir, but also these confining layers. So in fact, we're trying to measure the elastic parameters of the material, or poroelastic parameters, the permeability as well as relative permeability, because you will have the non-wetting fluid flowing on top of the wetting fluid in the reservoir. We also, depending on the material, of course, but we look at the microstructure to see if there are some fractures, some discontinuities that would contribute to the behavior of the material. And of course, we measure the triaxial strength. So a few kind of highlights on what really happens to rock when you inject CO2 into it. So for reservoir rock, it's usually sandstones and limestones that are relatively permeable and that are considered. And from our own experience, as well as what other people did over the last 20 years, we could say that for the reservoir that is made of sandstone, so quartz-rich material, we see very little effect on the properties of this material. For the material that is made of limestone, for the calcite-rich formations, there could be significantly strong chemical effects that would actually deteriorate the material properties. So here is the kind of example with one of the limestones that we used. So this one was relatively weak, as you can see, but also we can see that it's both the strength of the material as well as the stiffness, so Young's modulus in our case, that are changing significantly after we had, CO2 flowing through this rock for a few days. And then when we took our specimens off the cell, we could see that there is a significant a dissolution, especially at the point where we inject. And in fact, the porosity has significantly increased in this upstream channel. If we would have been using a more stronger limestone, the effect is smaller, like for Indiana limestone, but it's still there. Now for sandstone, we used a few. Here's the example with Berea sandstone. And in fact, when we just took like the pristine rock, we didn't see basically any effect. So we were injecting CO2 for a few weeks and nothing was happening. Then we decided to introduce like more damage into the rock. We put it in the oven, produced a lot of cracks. Then we started seeing some effect, but it was mainly in the creep, in the long-term response of the material, rather than the change in elastic properties of strength. So we think that sandstones in general are the good host formations if we really care about the integrity of the reservoir. I'm seeing that I'm running out of time, so just a few more things that I wanted to mention. So another thing, of course, is to ensure the integrity of the caprock. CO2 may reach the caprock when you inject, and it was the case actually in this very first Sleipner project, where they initially thought that the CO2 mixed with water will create a plume that will be more dense than the brine in the reservoir itself, and that will go to the bottom of the reservoir. But in fact, it quickly, the CO2 didn't completely dissolve, and it quickly, flew up and started propagating through for a few mudstone layers. So over the last few years, Norwegians are hiding the data, but it looks like there is the integrity of the caprock was actually not preserved. And of course, there are a lot of other things happening there, but it's very important to ensure that your caprock is very low permeable, as well as the size of the pores is small, such that the capillary effect doesn't let this non-wetting fluid CO2 to get into it. Another thing mainly with the caprock is that it's low permeable and locally deforming, or at a short time scale deforming under undrained condition. And also, of course, it's hotter than the CO2 that arrives to the caprock. So you can have the integrity of the material being questioned just because you are cooling it down quickly and the material responds in the undrained way. So we were trying to simulate some conditions at a relatively shallow depth of injection. For our particular case, we didn't really kind of question the integrity, but there could be cases where, so you see that kind of when you're cooling down, the Mohr circle is actually moving towards your failure envelope. So in some cases, you just by cooling down the caprock, you can fail it. Now, another thing that could happen due to this ductile behavior of the caprock is that you can, even in a very low permeable formation, you can actually create channels where CO2 can flow. And that's what also is probably happening at Sleipner, but we really need some data from them to make sure that it's in there. Now, in terms of the base rock, so it looked like, so from a number of pilot projects, the data was summarized by my friend and colleague, Victor Villarasa, and it was shown that so the sedimentary formations by themselves are far away of being critically stressed. And what I mean by that is that even from the yield surface, your Mohr circle is far away, and you really need to inject CO2 at very high overpressures, 10 MPa, which never happens, to question its integrity. However, the formations that lie underneath the sedimentary rock, the basement rock, could be close to be critically stressed. And that happens because by themselves, they're very strong. Cohesion could be 50, 80 MPa, friction angle 40, 50, but they have relatively weak faults where you can actually have some slippage. And of course, when fluid injection happens in a fracture, even if your initial state is far away from the critical state, you can quickly, increase the pore pressure in the fracture, and that would make some slippage, sliding happen, open the fracture and trigger microseismic events. And that's what oftentimes is referred as induced seismicity. In fact, induced seismicity is much more complicated. There are some poroelastoplastic effects, thermal effects, but like simple explanation is like this, that you basically move in your more circle towards your yield to failure surface. And so from our experience in Illinois Basin, we had a few projects already. The most famous was Illinois Basin Indicator project, where at the depth of 2.1 kilometer, the injection was happening in this lower Mount Simon formation, and for 3 years. Then it was some break. Now it's 3 more years, but we don't have the most recent data yet. So for the first stage of the project, there was a number of microseismic events, and of course the most the strongest one had a magnitude of 1.2. So it's not, we didn't really feel it here. But now the project is actually, we injecting like 3 times more in less permeable formation, so we can induce some stronger events. Now, it was, when the data was interpreted, it was found that actually most of the events are happening not in the reservoir and not even in this intermediate layer, which is less permeable underneath it, but in the basement rock. And the basement rock is very low permeable by itself. It has the permeability of sub-nanodarcy, so 10 to minus 22 meters squared. But all the specimens that we eventually managed to get from there, from this depth of more than 2 kilometers, have fractures. And these fractures appear to have almost zero cohesion, at least when we test them in the lab, and significantly smaller friction. So these fractures is what we believe are producing those microseismic events. And right now we're busy with characterizing what could really happen and predict some scenarios also for the safe injection, such that we don't induce very big events. So our approach is actually to look at the different scales, and we start from really a nanometer scale. We're doing porosimetry measurements and microphotographs to look how the rock looks like. We do some more or less standard rock testing. We're also involved in a tests which have a scale of a few meters, where we inject CO2 and study like the interaction of it with the cap rock and the host rock. And then of course we try to get the data from the big projects, but the first step here is to use the information, use the parameters that we measured, and then insert them in the numerical models and try to see what numerical models predict in terms of the reservoir and confining layers behavior. So now the next slide is slightly political in a way that the problem is quite complicated. We need a lot of projects. We need to inject a lot, and there will most likely will be problems with both, the cap rock, the reservoir, and the basement. So we still, of course, have to continue to do research in there, but we also need the help from the local as well as the federal government, in a way that we need to push for these projects, because we keep emitting more and more, we keep producing more and more waste, and the clock is ticking. There could be the point where, or maybe we're already at the point where it's irreversible and we change this planet forever. And of course, it takes the effort from all of us. We can blame politicians and other people, but we can also think about what we do every day and try to be more sustainable, use less energy, less water, more efficient and sustainable ways to transport yourself and do other things. And that slide concludes my talk. Thank you.